Welcome. Uh, this is a new module about linear algebra, and if we looked at the course catalog description, this is would be like our last module, like this linear algebra part. Okay. If you want to learn more or practice more about this topic, here are two references. This is your textbook. If you want to learn more about numerical solutions for linear algebra, like system of linear or nonlinear equations, you can system of linear equation and also nonlinear equations. You can check your textbook. If you want to learn more about analytical, like linear algebra in general and analytical solution, you can check this source also. Or you can any other similar sources that you have. Yeah. Okay. So linear algebra so far it's only one lesson. Uh, in this one lesson, I will be like a review of matrix operations. Uh, like some of you might have already covered this in Calc 3, but that would be like a review. And then we will look at the graphical, analytical, and numerical solution for a system of linear equation. And then we will do some critical thinking exercises like we'll look at two types of model, lumped variable system with coupled components. So here you have, like, for example, different lakes that are connected together or different uh, uh, tanks that are connected together. So a lumped system that is a system that has like input, output, and state. Yeah. Versus a distributed system that's not a lumped system. Yeah. So it is distributed in space basically. So it's not like a black box system, but more so lumped systems. That's like a black box system, like input, output, and the state of the system, whatever is happening inside. And there could be several of them that are connected together. Versus a distributed system, this is something that's distributed in space in X, Y, and Z. So it is not a black box. Yeah. And we will see like the difference between these two systems, like a lumped system and distributed variable system or a continuum. Yeah, and we will see how to use linear algebra to solve these types of problems. Anyway, without much talking, let's just start our one lesson so far in this topic, the introduction to linear algebra. So I will start by reviewing matrices operation. So in this part, basically, we will learn how to represent like linear algebraic equation or equations in the matrix form. Uh, that should be actually an S here is better, like linear algebraic equations in a matrix form. And then we will understand matrix notation and matrix operating rules, because you represent your system of equation in a matrix form. You don't represent it in this matrix form just for the fun of it, but because you want to solve this system. And we will learn about the notation and rules for these matrix operations to solve our system. So here, this is a matrix. So a matrix, what is a matrix? A matrix is a convenient method for representing a set of elements. So a set of elements, it could be numbers. So here, these are your uh, system parameters. And this here are like your system output, for example, and these are your system variables. So you have here two variables, x1 and x2. Yeah. Uh, so can we represent this in a matrix form? Yes, we can. So for example, I can represent this. I can take like these parameters and say like these are matrix A. So matrix A, that would be equal to, so my first equation, that's 4 and -5. And my second equation, that would be -2 and 3. So now I represented like these uh, parameters here. Yeah, this guy, this guy, this guy, and this guy. Can I represent also the right-hand side? Yes, I can. So the right-hand side, I can represent it in the matrix form. That would be negative 13 and 9. Yeah. Can I represent my variables, my system variables? I have two variables here, which are, I can call them x. Yeah. And that is like x1 and x2. Yeah, because I have x1 and x2. So now can I represent this equation in that form? I can say like a times x is equal to b. Yeah. So a times x is equal to b. A is a matrix, x is a matrix, and b is a matrix. Okay. Or alternatively, I can write it in this way. I can write it for negative 5 because that's a, negative 2 and 3 times x1 times x2, x1, x2 is equal to b, which is negative 13 over 9. Okay. So this is just like a way. So I have a system of linear equation, like 2, 3, whatever the number is. And oops, I have a fly on my screen, which I was trying to get rid of, but it seems that uh, it's just sticking and playing now on my screen. Anyway, uh, this baby fly. Okay, so this is just a way to represent my system of equations. So I have this system of equation. I just want to present it in this way. Yeah. Okay. So here is an practice problem for you. I'm telling you represent the system in equation in a matrix form. So I want to see if you can do this. So try to do this. Try to do it on your own. There are like some tricks here. I don't know if you will be able to figure them out on your own. Let me I will do this practice problem later, but just try to do this on your own and see if you'll get the answer correct or no. Okay. So like to represent this, that's basically like the answer. Yeah. Okay. And this is your homework. Represents the system of equation in the matrix form. Okay. Uh, Now let's so we will able to present like for example like this system of equation we were able to present it in this matrix form. So here's my parameters for example. So for x1 I have 1, for x2 I have 5, for x3 I have like 0 of them. My right hand side here is 0. Here for x1 I have 2, for x2 I have 0, for x3 I have 4, and so on and so forth. So and here I have three variables, x1, x2, and x3. So I was able to present this matrix as this form. Like, why am I doing this? I'm doing this because I want to solve for x1, x2, and x3. That's basically, I want to find like what is like x1, what is x2, and what is x3. So can I do this? Can I just by presenting it this form find x1 and x2 and x3? That's the main objective. Yes, I can do this. Not only that's one thing you can do when you represent this in a matrix form. One way you can find like this value, but there are other quantities that you can also quantify and learn about this system of equation. Like for example, the determinant of this system. Okay, which I will talk about in a minute. What's the determinant of a system? But before we do this, let's just learn about some matrix notation. So a matrix notation, like a matrix with n rows and n column, have the dimension n times n. So n, that is always the number of rows. So in that case, how many rows do I have here? I have one row. How many column I have? I have three. One, two, three. So this matrix, for example, like this is a row matrix with a size of 1 times 3. This is a column matrix. How many rows does it has? 1, 2, 3. How many column? Only one. So this is a column matrix with a size like 3 times 1. Uh, this is a square matrix. And what size does it has? It has like 1, 2, 3, and it has like 1, 2, 3. So this matrix A has a size of 3 times 3, for example. Here matrix A, here matrix A has a size 1 times 3, 3 times 1. I can do matrix transpose. So what is matrix transpose? Is basically like when you do like a matrix transpose, you just like rotate this guy in this direction. So in that case, like when I rotate this, so that would remain the same. Like, so this is like your pivot point, and then you rotate it around this guy. So, or actually, uh, yeah, so you just rotate, like you transpose it. So this would be here, this guy will be here, and this guy will be here. That's called the matrix transpose. This guy will be here, this guy will be here, and this guy will be here. This guy will be here, this guy will be here, this guy will be here. So basically, like you are converting a row to a column. Yeah. So basically, when you do the transpose of the matrix, your first row will become the first column. Your second row will become the second column, and your third row will become the third column. That's called like a matrix transpose, and we refer to it with like this T here. Yeah, A transpose. Okay. I mean, don't worry about like why these things are important now. Just like learn them, and later on I will show you why these things are important. Identity matrix. That is a matrix that has uh, 1 on the diagonal element. So all the diagonal elements are 1, and the off diagonal elements are 0. So these are off diagonal elements, these are off diagonal elements, these are 0, and like the diagonal element is 1. That's called an identity matrix. Upper triangle matrix, this is where all like this lower triangle is 0 here. That's called like an upper triangular matrix. Lower triangular matrix, this is when this upper triangle here is 0. Okay, so basically these are just some matrix notation, some matrix uh, jargons or whatever that you need to learn. Yeah, just you need to know. Yeah, so that we now one more thing we want also to learn about matrix, which is called like the determinant of a matrix. And the determinant of a matrix, here is an example. Yeah. So for example, like I have this matrix which is n times m. Okay. The determinant of and let me see here. The determinant of this matrix. Let me make a correction here. It's better to represent, or that's fine. Yeah. We like that. That's okay. That's okay. I can show it in this way. Yeah. So the determinant of a matrix. So the determinant of a square matrix, for example, that would be like a scalar value that provide like a important property of the matrix, such as whether this matrix is invertible. Invertible means like this matrix has some unique solution, as I will be discussing later when we get to this topic. Yeah. And also this determinant of the matrix, for example, that represent for like it has other also meanings that other than it tells you about the properties of the matrix. It could also have other meanings. So, for example, it could be tells you about like the scaling of a matrix, area or volume scaling. It could tell you about like the stability of the system. So if the zero determinant, like if I calculated the determinant of the matrix and the determinant is zero, for example, this tells me that this system of linear equation is not stable. So, for example, if I have a structure and I was able to represent this structure with the system of linear equation, and the determinant of I calculated the determinant of this matrix and it was zero, this will tell me that, for example, like this structure will not support this load, for example. That would be an example for the determinant of the matrix. Uh, uh, if I have like an image, for example, and let's say I transformed this image like to an image that's half of the side, the determinant of this transformation, like representing this transformation, that the matrix that represents this transformation, the determinant of this matrix will give you like the scaling factor. So if the scaling factor, if this image is half the size of like the original image, the determinant of this is, of this matrix, transforming matrix would be zero point 0.5, for example, or something like this. But anyway, this is not important. Like, the most important part is that like this the determinant of the matrix, we need this for the calculation step, and we need this, as I will show you later, and we will need this to know if the matrix is invertible. Invertible means that it has a unique solution. Yeah. We will talk about this later, but let's now not focus about the meaning of this, more focus on the mass of it. So the determinant of the matrix, it is expressed by these two uh, bars here that you see here. So for example, if I want to find the determinant of, so like this is matrix A, the determinant of matrix A would like be this bar, for example. If this is like say matrix B is equal to A, C, B, D. If I want like the determinant of matrix B, it would be like this bar A, C, B, D. Yeah, it would be like in this bar. That's how you, and how to calculate the determinant of the matrix. So like a matrix like this guy, the determinant of this matrix would be A times D minus B times C. That's basically how we do it. So what would be, let me delete this guy here. What is the determinant of this guy? So that would be like 4 times 1 minus 3 times 2. So that would be, so yeah, so here. So that would be 4 times 1, that's 4, 3 times 2, that's minus 6. So the determinant of this guy would be negative 2. Yeah, that's like the determinant of like a 2D matrix. For a 3D matrix, like how to find the determinant, let me show you. It's like you basically you do it like for each of these columns. So like for this guy, for example, like you cross it like this, and that would be like for this element here. So it's A time the determinant of this matrix. And we know the determinant of this matrix. So the determinant of this matrix, that would be E times I negative F times H. That would be the determinant of this matrix. Yeah. So basically, so that would be the first term here. Minus here, you do it like this. So that would be B negative. You put here negative B, and then that would be the determinant of like this guy and this guy here. So that is D and J. and that's F and I. Yeah. Similarly for C, you just cross it like this. Then you put here, this is negative, this is positive here, and this is positive here. Uh, so C, that would be like here, the determinant of this guy, D times E and D like this. So here's an example. So I'm telling you here what, so this is matrix A. So I'm telling you determinant of matrix A. So I'm giving you here an example like this matrix, like what is the determinant of, sorry, here that should be put like this because this is matrix B. The determinant of B, you should put it in this bar here. So the determinant, what is the determinant of matrix A? So can we do this? Yes. I mean, you don't need really to memorize this. You just can follow like this, whatever I told you. So that would be equal to what? So like let's start here. So that's like 2 times this guy. So that is 2 times the determinant of 5, 8, 6, 9. Yeah. So that is this guy. Time what? Like then you do this. So that is negative. Don't forget the negative 3 because we have 3 here, and the determinant of like 4 and 7 and 6 and 9. And then the last one is 1. So you cross this plus 1 and the determinant of 4 and 7 and 5 and 8. Yeah. So if you did this, can we calculate like this guy? Yeah, so this guy is 2 time, uh, so 5 time 9, that's like 45, negative 6 time 8, that is 48, yeah, negative 3, and that would be what? Like that would be 4 times 9, that is 36, negative 7 times 6, that is again, that is 42, okay, plus 1 time 4 times 8, that is like 32, negative 5 times 7, that's 35, yeah. So that is equal to this, so that's equal to what? So here that is equal to 2 times like negative 3, negative 3 times negative 6, yeah, and here plus 1 times what? This is negative 3, yeah, so that would be like negative 6 plus 18, negative 3, that would be 9, yeah. So the determinant of this guy is 9. So the determinant, remember, like, so the determinant, this is of a square matrix is a scalar value. It's a scalar value, it's not a matrix. That provide important property of the matrix, such as whether this matrix is invertible or not. So this matrix, the determinant is not 0, so this is invertible. So this system of equation has a unique solution. And it has a unique solution, and we can find like the inverse of this matrix, basically. Like invertible means like you can find the inverse of this matrix. Yeah. Okay. Okay, so we learned about some matrix notation. We learned about the determinant of a matrix. Now let's learn about some matrix algebra. Like, can we do like some matrix algebra? Yes. So if I have matrix A plus matrix B, that's equal to matrix B plus matrix A. Similarly, matrix A minus matrix B is equal to negative B plus A. So let's do an example here. So if I told you like matrix C is equal to A plus B, so can you find C? Yeah, so that's easy. So C would be, let me write it here. So matrix C is equal to matrix A, which is 4, negative 5, negative 2, 3, plus matrix B, which is 10, 20, 100, and like 200. Uh, so can we do this? Yeah, so that would be 4 plus 10, that's equal to what? That is equal 4 plus 10, that's 14. Negative 5 plus 20, that is 15. Negative 2 plus 100, that is 98. And 3 plus 200, that is 203. Yeah. So basically, that is how I was able to find C. Yeah. Uh, uh, Now the multiplication of a matrix. Uh, Let me do yeah, like the multiplication of a matrix. You can multiply like a matrix by constant. So matrix B, for example, is equal to constant time matrix A, or matrix A time a constant. So if I told you like this is matrix A here, and this is a constant, and I'm telling you what is matrix B. So that would be, you just multiply this by constant. So that would be 2 times 10, that's like 20. 10 times 3, that is 30. 10 times 4, that is 40. 10 times this, that's 200. 10 times, that's like this. That's like another 300. 10 times 10, that's like 100, 100, and 100. Okay, so basically that is when you multiply a matrix by constant. Yeah, so it really doesn't matter. But now here is the important part. Matrix A time matrix B, the multiplication of matrix A with B, is not equal to the multiplication of B with A. Why is that? Because my matrix multiplication, that is, we do this differently. So matrix multiplication, if I want to multiply like this matrix, so this is matrix A, which is, what is the size of this matrix? So this is like 3 by 3. Why? Because I have like 3 of them here, and I have like 3 of them here. What is the size of this matrix? So the size of this matrix, this is 3. I have like 3 rows times 2 columns. Okay. So in order for the matrix to be multiplied, okay, it requires that the number of columns of matrix 1, which is 3, is equal to the number of rows of matrix 2, which is 3 here. So if like these two guys are equal, now here's the rule. This is a multiplication rule. If these two guys are equal, this means I can multiply like this matrix A with matrix B, and the product matrix will have this size, 3 times 2. And that's exactly what we got here. So we got like this matrix is 3 rows times 2 column. Okay, so let me do this again. So here I have like 3 by 3 matrix. This is like 3 rows and 2 column matrix. If I multiply this together, can I multiply this together? Yes, because like these two guys are equal. What would be the size of the resultant matrix? It will be like these two guys, 3 times 2, which is exactly what I got here. But how do I do this multiplication? So to do this multiplication, basically, you multiply like this guy with this guy, and that will give you, for example, this guy. Yeah. You multiply like this guy, yeah, with this guy, and that will give you this guy here. Okay. Now, similarly, you multiply like this guy with this guy, and that will give you this guy here. You multiply like this guy with this guy, and that will give you this guy here. You multiply like this guy with this guy here, and then you multiply like this guy with this guy, and that will give you the last guy here. So that's basically how we do this. Can we try this? Yes. So here's an example. This is like matrix A times matrix B is equal to matrix C. So what is matrix C? So matrix C, remember again, like that would be equal to like the first element here in the first row and first column. So that would be like the multiplication of this guy times this guy. So can we do it? So that is what? That is 2 times 3 plus 3 times 4 plus 4 times 5. So that's equal to what? That's equal to 6. And that's equal to 12. And that's equal to what? That's equal to 20. So can I add these guys together? So if I added this, that is 18 and that's 20. So I got like 38. So I have 38 here. Yeah, that's basically how you do it. And let's do the second element. Yeah. So the second element will be like this guy times this guy. So can I do this? So that is like 2 times 2 plus 3 times 2 plus 4 times 2. Can I do this? So that is 4 plus 12 plus 8. So that would be 24. No, sorry. Like 2 times 2, that's 4. 3 times 2, that is not, that's 6. And 4 times 2, that is 8. So that is, will give me like 18. So this guy here is 18. Yeah. I mean, is this fun? I mean, it's fun. I mean, it's not difficult. Just make sure you don't make silly mistakes. Let's see how we are doing in time. I don't want to keep all the time is, yeah. Anyway, we still like have some time. Okay, I mean, I don't want to keep this for long, but let's do this guy here. Yeah, so like if you want to find like so you multiply this guy by this guy so that if I want to find like this value here, I will just do this as the last one. So like to find this value here, you multiply this guy by this guy. So that would be like 20 times 3 plus 30 times 4 plus 30 times 5. So that would be like 60. That would be 120. And that would be like 150. Yeah. So if we did this, so that will give us 180 and plus 150. That is 380 plus 150. That's 330. So that will be like 330. Yeah. Okay. And me just like in order not to keep this video long. So like to get like this guy here, how do you do this? You multiply this guy by this guy. So if you did this, you will get like 160, and then you multiply this guy by this guy. If you did this, you get 120 here, and then you multiply this guy by this guy, and if you did this, you will get 60 here. Okay. So basically, now is why these are not equal, like why a times b is not equal to b times c, because b times c I cannot even multiply because b have a size of what? B has a size of 3 times 2 and a has a size of what? Sorry, it's not equal to b times a. uh, b has a size of 3 times 2, yeah, and a has a size of 3 times 3. So can I multiply these matrices? No, because these two are not equal. Like for these matrices to be multiplied together, these two needs to be equal. And that's why A times B does not equal to B times A. Yeah. I mean, let me just practice here. Yeah. So this is matrix A. Here have a size of what? So this have a size of 3 times 3. And matrix B has a size of 3 times 2. So like you see, these two guys are equal. Yeah. So see, these two guys are equal. And the resulting matrix C will have the size of like 3 times 2, which is what we got here. How about this guy? So here, like the first matrix, my matrix A, it has a size of 3 times 2. And my matrix B has a size also of 3 times 2. Can I multiply these matrices? No. So these two matrices, uh, I cannot multiply it, like not possible to multiply them, not possible to multiply them because this is not equal to this. How about this guy? What is the size of this guy? So the size of this guy is 1 times 3. And what's the size of this guy? The size of this guy is like 3 times 2. So is this, can I multiply this? Yes, because here 3 is equal to 3. What would be the size of the remaining of the product of like these two matrices? The size would be like 1 times 2. So if I multiply this together, try to do it, the answer would be like 38 and 18. So basically, like you multiply this guy by this guy, you get the 38. Then you multiply this guy by this guy, you get like the 18 here. Yeah. And that's how you can do this. Okay. Now, let us do one more. So here is one more. Let's do this guy. So this guy, what is the size of this guy? This is like 1 times 3 multiplied by what? Multiplied by 3 times 1. So can we multiply this? Yes, we can multiply this. And what would be the size of the remaining matrix? 1. Just one element, like scalar. And how to do this? Basically, like you just multiply this guy by this guy, and that will give you just one number, which is 20. Because when you multiply this guy, that's like 2 times 1 plus 3 times 2 plus 4 times 3 times 3. And that is equal to, so this is 2 plus 6 plus 12, and that is equal to 20. So you just get like scalar, and that's like 1 by 1. Yeah, it's 1 by 1, one row and one. Yeah, but it's just a scalar. You don't need to present it as a matrix. Yeah. Okay. So basically, so now you are expert in matrix addition and matrix multiplication, and you know that the most important thing about matrix multiplication, this is not like algebra. Like in algebra, A, that's in algebra, regular algebra, like A times B is equal to B times A. In linear algebra, A times B is not equal to B times A. Because this is an algebra, this is just like scalar, but here this is a matrix, this is a matrix, this is a matrix, this is a matrix, yeah. So this is algebra, this is here linear algebra, yeah. Okay, so that's like one of the take-home message that you need to take here, yeah, to know here. Okay, let's can we like similar to what we did, like we multiplied matrix, can we also divide two matrices? No. So matrix operation rule, if a matrix is a square and it's non-singular, non-singular means that it is invertible, means that like its determinant is not equal to 0. There is another matrix called inverse matrix, but there's no such thing as matrix division, but we can do an inverse matrix. So this is, you can think of this as analogous to division in the sense that the number divided by itself is 1, but it's not actually division. This is called like inverse matrix. So what does this mean? So basically here is the rule. So the rule is if I have a matrix times the inverse of this matrix, that is equal to the inverse of this matrix times this matrix, and that's equal to an identity matrix. And you know what's an identity matrix? Identity matrix, that's a matrix that has 1 in the diagonal element and 0 in the off diagonal element. So in 3D, like if it's 3 by 3, for example, it would be something like this, yeah? So that's like an identity matrix, yeah? That's an identity matrix. So that is the main rule here. A matrix multiplied by the inverse of the matrix is equal to the inverse of the matrix multiplied by the matrix is equal to an identity matrix. But the question is, how can I find like this inverse of this matrix? Like we learned how to do product of two matrix, but how to find the inverse of the matrix? So basically, for a matrix that's like square matrix that is 2 by 2, the inverse of the matrix is takes like this form. Yeah, that's how you can find the inverse of the matrix. So uh, that is basically, so can we do this? Like, can we find the inverse of this guy? Yeah. So you can say like the inverse of A, that is equal to the determinant of A. You know what is the determinant of A? Yeah, you are expert in this. So that would be like this guy times this guy minus this guy times this guy. So that would be uh, 4 times 6 minus 7 times 2. Yeah. 4 times 6 minus 7 times 2. So that is the determinant of this matrix time. Uh, uh, so here it's like this is the D here. So that would be like this guy minus B. So that is B here. So that would be minus 7 minus C. So that is C here. So that is negative 2. And A, that is A here. So would be something like this. Yeah. So like you see how I did it. So that's A. So it will be something like this. So can I do this? Yes, I can. Oops, I can do this. So that would be what? So here that would be 1 over so this is 24 minus 14. So 24 minus 14, that's 10. So 1 over 10 time 6 over negative 2, negative 7 times 4. And we know that we can multiply this because this is a constant, so I can multiply this by a constant. So that would be 0.6, negative 0.2, negative 0.7, and 0.4. So now I was able to define the inverse of the matrix. And it's non-singular. Why non-singular? Because the determinant does not equal 0. Because if the determinant, that's the determinant. If that's equal to 0, then you will multiply this by 0. You will get a 0. But here the determinant, like here the determinant A does not equal to 0. Okay? So can we verify that, like, how would you know that this is the correct answer? Like, that this is the correct answer? Well, I can verify it by this rule. So I can say like A times the inverse of the matrix, I should get an identity matrix. So can we do this? Yes, let's try to do it. So A, that is, what's my matrix? So A is 4, oops, that is like 4, 7, and 6. Okay, time the inverse, that's 0.6, negative 0.2, negative 0.7, 0.4. So if I did this multiplication, and like this multiplication give me something that's like 1, 1, and 0, 0, this means that this is like I did something correct here. Yeah. So here, so this means that I did something correct. So let's do it. Yeah. So how to remember like how to do it? So basically like you multiply like this guy by this guy to find this element. So that is 4 times 0.6, that's like 2.4, negative 7 multiplied by this, so that would be negative 1.4. That's like here, the first element. The second element here, that would be 4 times negative 0.7, so you get like negative 2.8, and then that would be 7 time zero point 0.4, so I will get plus you see here now I started to see my 0, and here I started to see my 1s. So let's do this one here. So like this guy here, that would be like this guy multiplied by this guy. So this guy multiplied by this guy, I got like 1.2 here, and then I got 6 times this, I got negative 1.2 here. I start to see the other 0 here. And then like finally, like my last element would be like this guy multiplied by this guy. So I have 2 times negative 0.7, so I got like negative 1.4, and then 6 times 0.4, so that is like 2.4. And what did I get? I got it, yeah, because this guy minus this guy, that give me 1. This guy minus this guy, that give me 0. This guy minus this guy, that give me 0. This guy minus this guy, that give me 1. So I got an identity matrix, and this is so now this means that like this guy is the inverse of this guy, because when I multiply them together, I got an identity matrix. Let's see how we are doing in time. Okay, not perfect, but it's okay. So can we also do an identity matrix for sorry, find like the inverse matrix for if my matrix is like more than 2 by 2, like 3 by 3, 4 by 4? Yeah, it's more involved. It is it's just more involved. So basically, like if you want to do this, if this is your matrix, yeah, like it's 3 by 3 here, and then you want to find the identity matrix. So the identity matrix, that would be the adjoint matrix, which is the transpose of something called the cofactor matrix. And what is this cofactor matrix? This is how this cofactor matrix looks like. So basically, that is like, you see this element here, for example, would be like you do this, and that would be like this guy. That would be this element here. Yeah. This element here, like you see the negative sign. There is a rule for this negative sign, by the way, but like it's not important. Like here, this is a rule for this negative sign. But what is this guy? This guy would be basically like here, like it is this guy and this guy. That will give you like this guy here. And similarly, uh, like for this one, so you multiply, so you here this guy, that would be like this guy here. And how do you know that this is positive or negative? So basically, there's a rule here, like it's negative 1 times n times m. So like let me show you like how to know if this is positive or negative. So here n is equal to 1 and m is equal to 1, so that is negative 1 times 2, and that's why you got a positive. Here, for example, uh, n negative 1, n is equal to 1, m is equal to 2, because this is the second column, so I got like equal to 1, negative 1 to the power of 3, then I got negative 1. That's why I have a negative here. So you see like uh, this positive and negative, it follows this rule. Yeah. That's basically the rules that this thing follow. But anyway, these details are not important. For example, like if I want to get this guy, that would be what? So that would be like here. So that would be this guy. And that will be like here, this guy here. Okay. But again, these details are not important. And this is just extra and optional. Like you just become familiar with it. Like typically, we solve these things with we don't solve these things by hand, but we typically solve this thing using a programming language, yeah. And like MATLAB or Python. You can also solve this with Excel. So Excel also has can solve matrices. I will show you like how to solve this with Excel. But here, if you want to do like an example, you don't need to do it. This is optional and extra. So this is the matrix A. This is a cofactor matrix C, and then you transpose this cofactor matrix. And remember, what's a matrix transpose? Matrix transpose means that this column will become this row, this column will become this row, and this column will become this row. That's the matrix transpose. So you transpose the, the adjoint matrix as the transpose of the cofactor matrix. And then to find the inverse, you divide the adjoint matrix by the determinant of the matrix. So you have to calculate like the determinant of the matrix. So basically, you divide like this guy by 9, and then that would be the inverse of this matrix. Yeah. And we typically solve this numerically. Yeah. Or with the calculator, like if your calculator can do this also. Okay. So here is a practice. So like I want you to just like pause this video and try to do this. So this is matrix A and matrix B, and I'm telling you matrix C is equal to matrix A plus B. You see here, this is in a capital, in a caps letter. Like this is a small font, but this is a caps, like a bold font, because 2 signifies that this is a matrix. So this bold font means that this is a matrix. Yeah, this bold font here. So I'm telling you what is matrix C is equal to A plus B. So try to do this. And I'm telling you matrix D is equal to A times B. So try to find matrix D and also find the inverse of matrix A. And I'm giving you the rule here for the inverse of matrix A. So pause this video, try to do it. And if I did this correct, this is the answer that I got. Yeah. And if you can do this, you have a similar homework problem which you can also do. Yeah. So this is this guy here. This is this guy here. Okay, so I think that's all for this video, and where we reviewed the matrix operations and matrix notation, and I will see you in the next video.